Assalamualaikum and hi. This is chapter 4 steam turbine cycle for part 6 video for the example question. Okay, this is the example 4.5. First, I will read the question. Consider a steam power plant operating on the ideal regenerative Rankine cycle with one open feed water heater. The steam enters the turbine at 50 MPa and 600 degrees Celsius and is condensed in the condenser at the pressure of 10 kPa. Some steam leave the turbine at the pressure of 1.2 megapascal and enter the open feed water heater. Determine the fraction of steam extracted, which is the Y, from the turbine, and the thermal efficiency of the cycle, which is the thermal efficiency of the cycle. So after we read the question, we should list down all the information given, which I will show you in the next slide. So based on the question, first withdraw the open feed water diagram, simplify of the open feed water diagram, and also withdraw the TS diagram. And from this figure and from the information we get from the question, we know that the condenser is at 10 kPa and the feed water heater is at 1.2 megapascal. Since this is an open feed water heater, the pressure at state 3 also 1.2 and the pressure at state 4 before the boiler is 15 megapascal, and at state 5 also 15 megapascal, and the inlet temperature of the turbine is 500 degrees Celsius and the bleeding pressure is 1.2 megapascal. So, and we know that the outlet at the state 7 is 10 kPa, and this is all the information given based on the question. And we know that from the TS diagram, we know that state 1 is here, and then goes into the, which is at the 10 kPa, and state 2 and state 3 at 1.2 megapascal, and state 4 is 15 megapascal, and we know there is the state 5 which is at the 600 degrees Celsius, and state 6, and then state 7. And the question asks which is Y value at state 6, which is the ratio of the mass, bleeding mass at state 6, and the thermal efficiency of the system. Okay, so this is all the information given and what the question want the answer. So first, we look into the determine the fraction of steam extracted from the turbine and the thermal efficiency of the cycle. Okay, we already extract all the information from the question, and we already draw the TS diagram, also simplify diagram of the ideal regenerative open feed water system. And the data given here is P4 equal to P5 and it is equal to 15 megapascal, since state 4 and state 5 at the same saturated constant pressure line, and then P1 equal to P7 and it is at 10 kPa, same with the this is at the constant pressure line of the heat rejection process. And then we know that P6, P3, P2 is equal to 1.2 megapascal, which is given in the question. And temperature at state 6 is 600 degrees Celsius. And from the thermal efficiency, we know that work net divided by Q in is equal to 1 minus Q out divided by Q in. So first we look into the state 1, which is at the P equal to 10 kPa. And we know that it is at the saturated liquid, exactly at the saturated liquid line. And at the 10 kPa, we look into the saturated water pressure table. At 10 kPa, the value of the enthalpy is at the HF, which is the saturated liquid line, and is equal to 191.83. And the specific volume, which is the VF, if we're looking at the this table, the 10 kPa, the VF, which is the specific volume of the steam, and the enthalpy also at here, and goes into the state 2, which is the process isentropic process. And since it is an isentropic compression process, we know that the entropy at state 1 and state 2 is equal, and we also know that the pressure is equal to 1.2 megapascal. So here we know that the process is in the compressed liquid state, and from the equation of work pump in is equal to V1, which is the specific volume at state 1 times in the bracket P2 minus P1. It also equal to H2 minus H1. And from this calculation, we get the work pump in is equal to 1.2 kilojoule per kg. Okay, so we already know this value, which is the specific volume here of state 1. And we also know the pressure at state 2, which is 1.2 megapascal. And we know the pressure at state 1, which is the 10 kPa. And from this equation, we can calculate the work pump in of the pump 1. And from here also, we can calculate the H2. Since we know the H1, which is the enthalpy at state 1 here, we can calculate H2. Moving forward, we goes into the state 3, which is at the saturated liquid line, and the pressure at state 3 is 1.2 megapascal. And since it's at the saturated liquid line, we look into the 1.2 megapascal of the saturated water pressure table, and we can extract the information from the table, which is 1.2 megapascal. We know that the HF is 7698 because it is exactly on the saturated liquid line, and the specific volume is this value. And so now we move to the state 4, which is process 3 to 4, which is another isentropic process, isentropic compression process from pump 2. And we know that pressure at state 4 is 15 megapascal, and entropy at state 4 and state 3 is equal. And we know that this process happen in the compressed liquid region, and from the work pump in, which is equal to V3, which is the specific volume at state 3 times in the bracket P4 minus P3, and it is equal to H4 minus H3, and it is equal to 15.73 kilojoule per kg. We already know all this information. We just input it into this information, and we can calculate the work pump in. And from this work pump in, we can calculate the enthalpy at state 4, which is equal to 114 0.39 kilojoule per kg. Moving on to the state 5, we already know that the pressure is equal to 50 megapascal, and the temperature at state 5 is equal to 600 degrees Celsius, and it is at the superheated vapor process. Actually, before we justify it is in the superheated vapor, we should look into the 50 megapascal saturated water table. For the pressure table, we look there whether the temperature is saturated temperature is higher or lower than the 600 degrees Celsius. However, for this case, we know that the state as state 5 is the superheated vapor, so we straight away look into the superheated table at the 50 megapascal pressure of 50 megapascal and temperature of 600 degrees Celsius, so we can know the temperature value of V, H, and also entropy. So here H5 is equal to 3582.3 kilojoule per kg, and the S at state 5 is equal to 6.6776 kilojoule per kg dot Kelvin. And now we move to the state 6, which is the isentropic process of 5 to 6. P6 is equal to 1.2 megapascal, and S6 is equal to S5, and it is equal to 6.6776 kilojoule per kg dot Kelvin. And from the saturated water pressure table, we look into the 1.2 megapascal, and from this figure, from this table, we know that the entropy, which is 6.6776, is larger than the saturated vapor 6.5233. So we know that this state is in the superheated phase, superheated vapor phase, so we should look into the superheated table. And we know that it is in the we look at the pressure of 1.2 megapascal, and as you can see here, the entropy of 6.6776 is in between these two value, which is at the temperature of 200 Kelvin and also 200 degrees Celsius and also 250 degrees Celsius. So we need to do the interpolation to know the exact value of the temperature and the H value. Okay, here. So from the interpolation, we know that the enthalpy at state C is 2859.54 kilojoule per kg. Now we're moving forward to the state 7, which is the isentropic process of state 6 to 7. And we know that the pressure at state 7 is 10 kPa, and the entropy of 7 and 6 is equal to 6.6776 kilojoule per kg dot Kelvin. And we know that it is in the in between the or it is in the saturated mixture condition. So we look into the 10 kPa first here, and then we look into the entropy value, which is in the range of these two, in the middle, somewhere in the middle between these two. So it is in the saturated mixture region. So we can, from the this equation, we can calculate the and x value, which is 0.8037, and we also can calculate the enthalpy at state 7 and also entropy at state 7. We already know the entropy at state 7, so we just need to calculate the enthalpy at state 7. Okay, so we already calculate all the value, and we also know the data given from the question. So we just need to list down all the question there. So the data given from the question and also the calculated data, which we calculate from the analysis of the TS diagram. And we know this is an open feed water heater, which is a mixing chamber. So the energy in mass flow rate, energy in is equal to energy out. And we can convert it into the summation of mass flow rate in time enthalpy in. It is equal to summation of mass flow rate out times the enthalpy of the system. So for the mixing chamber, we have a mass flow rate from the enthalpy at state 6 and also enthalpy from state 2. Okay, uh, so this is the final product of the mixing chamber. So we have one enthalpy from state 2 and also one from state 6, and we know that the ratio of the mass is y here, and this one is 1 minus y. So from this equation we can derive this equation, and we can just input all the value there. So from there we know that y is equal to h3 minus h2 divided by h6 minus h2, and we can calculate the value of y from this equation. And from since we already know all the information, we can calculate the q in and also q out, and from these two information we can calculate the thermal efficiency of the system, which is 46.3%. So this is the all the answer for question 4.5.